Okay, hello
All right.
everyone. Welcome back to the AutoML seminar. It's my great pleasure to have Leonard here again, the second time. And he's going to talk about how we can use visualization to optimize our prompts for large language models. And this is work that he did at AWS Berlin during his internship there. And yeah, without any further ado, thanks a lot, Leonard, and take it from here.
Thanks, Aaron. So, hi everyone. As Aaron said, this was done during my internship at AWS. I'm quite happy that it actually recently got accepted at ICML. It's a paper that uses AutoML techniques or is inspired from AutoML techniques for an application field where maybe AutoML hasn't done that much yet, but I believe things are actually an interesting venue or playground. And it's about prompt selection with LLMs. So of course, if you work with foundation models, probably in the talk, you should generate a high-level image with another foundation model, right? So this is what GPT-4o, the image model, came up with. But the paper, so actually gives a quite decent overview. So assume we have a black box LLM, the black box, right? It's only queryable via API. We assume it's a total black box, could be hosted, for example, on AWS Bedrock. You do not have access to anything except for you give it input, you get output. And we know that for a downstream task like problem solving or any other downstream task, could also be a simple classification, you usually play around with the prompt, right? So you have input, natural language input, you want natural language output, but you also format the task input with a prompt that could be composed of an instruction, basically telling the LLM how to solve a task and what the goal is, and then some K-shot examples that you have access to, usually labeled ones, right? So given some examples of a task, for example, some math solving task, you include some examples. This is a math problem, and this is how you solve it step by step, and this is the correct output line. So the LLM does some in-context learning based on the downstream task. And the paper is mainly about if we focus on a setting that a prompt is composed of an instruction and a few-shot exemplar, and by exemplar, we mean it's a k-tuple of examples, and the ordering matters. If a prompt is composed of these building blocks, is there any efficient way if we have some instructions and we have some of these few-shot exemplars and we would combine them to get the search space, like what's an efficient way to automatically identify a well-performing prompt? And it's about doing this efficiently. So you want to use a low query budget when querying the LLM, and you want to do it automatically in a smart way, right? Okay, so the presentation will be mainly brief problem statement, although I think it's mostly clear, like from a high level, what we are doing in the paper. Then some background and taxonomy, because prompt optimization, prompt selection has been a field where lots of work has been done the last years, like 2 or 3 years already, but still a lot of work is being done. And some taxonomy is actually useful, I would say, to categorize existing related work. Then I'm going to talk about how HbBoPs, which is just like hyperband Bayesian optimization prompt selection, how the method works. And then I show you the experimental setup and benchmarks, results and analysis, and some conclusions. All right, problem statement. So like I said, we have an LLM. It's a black box. We will see this during the taxonomy slide. So you give it input, you get output. That's all you get. And we assume that prompts are composed of instructions and few-shot exemplars. That's a somewhat limited setting. Naturally, you could include more. We'll discuss this later. For example, output guidance, formatting instructions. But it actually goes beyond what most of the recent work with prompt selection or optimization has been concerned with, since they mostly focused on instructions only. So a lot of papers have been out there. How can I automatically identify or generate a good instruction for a downstream task? So we have the setting, you have instructions and few-shot exemplars, you combine them, and you want to identify the best prompt that performs best in expectation on a downstream task. In academic benchmarks, the downstream task could be GSM-8K, right, where you have math problems that involve some steps to solve it. And yeah, performance can be measured by performance metric. We'll see this later. But diagnostic cases, you want to have a good prompt, right, on a downstream task. This is a setting we will later see that's then black box because the LLM is treated as a total black box. That's why the AutoML part becomes interesting. And it's a static setting. We will see how this is different to a dynamic setting. And it's a selection setting because we currently assume you have a pool of candidate prompts that doesn't evolve over time, but it could be extended to a dynamic setting. So if you are in this setting that is static black box prompt selection, what you usually do is you need access to a validation set. Again, labeled input-output examples of the task, what the LLM should return for an instance of the task. And then you try out different prompts, you evaluate the prompts on the validation set. And in the end, you try to find the prompt that performs best. You could do this exhaustively if you have a finite search space. Try out all prompts on all validation instances, but this is costly, right? This means you usually have a lot of validation instances, or hopefully a lot, maybe 100. You have many prompts. This means you would now do all LLM calls for all prompts on all instances, compute the metric, and then get the best one. That's not efficient because LLM querying is costly, especially if it's like well-performing models, and it's also a little time-consuming, right? But also the monetary cost. If you treat the LLM as a black box API, you have to pay, right, for each token or each query that you do. Okay, formally this means we have a prompt search space that capitalized the calligraphic P. We have prompts, and we have an expectation over X would be the input to a task, Y would be the output to a task, and then you need some loss function or performance metric that is point-wise, where you compare the ground truth output to what the LLM H configured to use prompt P gives you if you feed it input X. It's just some formalization, but it looks quite familiar to what you usually see also in other black box optimization problems, right? So we would like to find the prompt that in expectation performs well for all samples from a downstream task, but in practice we cannot, of course, optimize the expectation. So we approximate it based on this finite validation set. So we have n-valid samples in your validation set, then you just take the empirical mean of the performance. I don't want to talk about a performance evaluation in general in LLMs. A very typical loss function is actually exact match. I'm not too much a fan of, but that's what lots of people do in academic benchmarks. So you just compare the Y, which is still natural language, to the natural language output of the LLM, and then you do an exact match comparison of the natural language, so the character, so to speak. This means you need to do some output sanitation and some output formatting probably also to get this working. You could come up with other loss functions that give rise to performance metric, but exact match is something that you could actually think about in the setting. And then you would have something like an error rate, so to speak, that you minimize, right? If you frame the loss like a loss of 0 if it's the same output, a loss of 1 if it's not the same. Okay, I already mentioned a lot about like black box selection, optimization, dynamic. So if you do a literature search or review of prompt optimization and selection, you can come up with like different types of work and categorization along different dimensions. So let's briefly go over it to give you actually a better understanding in which dimension does our work fall into. So you can either treat the LLM as black box. This means you only have access to model outputs via API. You don't have like any gradient information, and you don't even assume access to token probabilities, like the very black box setting. That usually means if you want to find a good prompt, you need some query efficient derivative-free method, because the only thing you can do is try out a prompt on some instances, and this is the signal you optimize. You could frame it as a white box setting if you do have access to a white box LLM that is like also self-host, then you could actually compute gradients, right, with respect to the loss function. It's fully differentiable. But for this setting where we assume someone hosts the LLM, it's much more reasonable to assume the black box setting. But if you had access to the LLM and you host it yourself and it's an open weight model, or you do have access to it, then you could actually do gradient-based prompt optimization or selection. And there has been some work on this. The other main dimension you can categorize the work is it static or is it dynamic? So static means I want to find a single prompt offline. So before I deploy the prompt that is composed of an instruction and a future exemplar, I do offline optimization. I have access to some validation instances as a proxy, and I want to find the best prompt on these instances. I do it offline, and once I identify the best prompt, I'm done, and I deploy the prompt in my pipeline. This usually means you prioritize robustness and average case performance because, well, you do not adapt to each test instance individually. So you assume that instances are quite homogeneous and there's one prompt that performs on average very well. And this is what you're going to do. The other thing you could do would be dynamic, and this means you do it online. So prompts are selected or adapted per test instance. So your pipeline sees there's an X coming in of a task. Then your recommender system or whatever you learned offline, could be reinforcement learned agent, I don't know. It selects adaptively for each instance a prompt or builds it, so to speak, online in an online fashion. This has the advantage that performance should be better because you can tailor to prompts, but it usually does add some latency. And you need to be careful how you do like learn the system that recommends then, for example, future examples adaptively or instructions adaptively to a prompt. But this is what you call the dynamic setting. And this allows for instance-specific reasoning. And usually this means better accuracy in the case of exact match or like better performance in general. But it's not something you would do easily offline and then just deploy the prompt and no longer care. And then there's selection versus optimization. So selection means we have a predefined finite set of prompts. In our setting where we are concerned with instructions and future exemplars, this is quite reasonable. So you can come up with 5 to 10 different instructions manually or use some automatic instruction techniques. And then you have some future examples that you try out in a different order. This builds your exemplars, and then you usually just combine them, right? You can do a brute force Cartesian product, and that quickly gives you a large discrete search space. But that is predefined and a finite set, and you assume one of these prompts is well performed. That means I don't care about like during optimization or selection generating new prompts, better prompts, but I mostly care about efficiently evaluating and ranking the prompts in my search space to quickly identify the best performance. And the other one would be optimization, where you generate or refine new prompts during the process, the offline process. This usually means if you do have access to gradients, you use some gradient-based method, or very popularly, you do evolutionary optimization on the prompts, like mutate prompts in natural language, come up with new ones during optimization, and then evolve the prompt space, so to speak, over time. All right, and we are focused on black box static selection. And there is some related work actually. MIPRO, which is from DSPy, and EASE and the triple class of algorithms. Mostly what we found interesting is when I started the project, 2 or 3 of these were actually still under review. So although you would think prompt optimization or selection goes back 2 or 3 years now, there has been quite some very recent work. So MIPRO was published recently, EASE and triple also, actually both at NeurIPS, which is maybe surprising or not, but it shows that there's still some interest in how to efficiently identify prompts. Okay, so MIPRO is DSPy is what they call teleprompter. So DSPy is this pipeline, basically software pipeline around LLMs. Probably some of you have used before. And they also have the use case of generate some instructions, generate some future examples, or you tell them, and then they want to efficiently identify the best performing one within the pipeline. And to do this, they have MIPRO version 2 actually. And the search space is similar to ours, so they combine instructions with future exemplars from a finite pool. And what they then do is they use a tree-structured Parson estimate. So some version of Bayesian optimization. But how they actually train the surrogate model is they use categorical indices. So assume you have some instructions, instruction 1 to 5, you have future exemplars, I don't know, 1 to 100, and then they try to learn a model on these indices, categorical or integer-based ones. Some limitations, you completely ignore that prompts are natural language, and there's like some semantic meaning, and some prompts are similar to each other, some instructions are similar, others are not, and the same for future examples. This is something an index cannot capture at all, right? And how they do the evaluation is, it's not what we call query efficient, because they still, like all the black box methods that are done offline, in a static case, you need access to a validation set. The question is now, how can I speed this evaluation up? Like if I have 100, 1000 validation instances, do I evaluate each prompt on all, or do I do something smarter? And what they do is they evaluate all prompts on all validation instances and maybe subsample, but keep the same random subsample of validation instances. But it's not really query efficient, which we'll see later. Where query efficiency means I do not want to evaluate all prompts on all instances, but save LLM calls or token cost. Then there's ease. They are mainly concerned with actually exemplar selection, but still fall in the static black box prompt selection. And they use neural UCB. So it's also Bayesian optimization or bandit-related optimization algorithm based on the upper confidence bound, and use embeddings of prompts. Prompt is treated as a block of text. You use an embedding of a pre-trained encoder model, could be BERT, and then you learn a surrogate model based on the neural UCB approach, which is in essence like a neural network surrogate model. And this maps you then prompts in natural language after you have embedded them to downstream performance. Since they are mostly concerned with how to select exemplars, and they assume you might have a huge few-shot example space. So assume you have like 1,000 examples and you want to pick 5, it's a huge combinatorial problem, right? Which one you pick, but also in which order you present them. And then they introduce some optimal transport heuristic to prune the exemplar space actually during optimization. This is their main contribution, but still you can actually employ it in this instruction and few-shot exemplar setting in which we operate. Limitations, they do not make use of separate building blocks of prompts. If they work with instructions and exemplars, they simply treat the prompt as a block of text and embed it. And the other thing again is evaluation is not query efficient. They either evaluate all prompts on all validation instances or they use a random subset. We might actually have time to see why a random subset can be highly problematic later on. Like if you sample 10 or 20 instances, you will see, or we can see that the optimization that the objective that you're optimizing is actually quite noisy, and you end up with quite some generalization gap. And the last one is triple related work. They actually made a more direct connection also to AutoML techniques and identified prompt selection as a multi-arm bandit problem. And then use successive halving. So here pulling an arm means I evaluate a prompt on one instance. And then you can frame it as a multi-arm bandit problem, and they simply use successive halving, so nothing fancy, and generalized successive elimination. That's also an existing bandit algorithm. The idea is in successive halving, you would discard based on the observed mean performance. In GSE, you would eliminate based on the expected performance based on a surrogate model, so to speak. So there's some similarity to what we do and also what EASE does. In general, the question is, can I learn a mapping from surrogate, from prompts to performance? And how can I speed up evaluation of prompts? Exactly. For the GSE, triple actually uses also embeddings of prompts, limitations. The way how they use successive halving can be, or in general, it can be quite sensitive to initial budgets. Those familiar with hyperband versus successive halving probably know this. We will see this later. The question is how many instances do I give the prompts when I start before I discard the worst performing half? And they do not make use again of building blocks of prompts. So for most of the methods, the prompt is just it's some natural language block of text that I can embed maybe and work with. And again, although better, they actually run successive halving that they start with evaluating all prompts. You don't have to do this necessarily, but they emphasize this in the implementation paper. So you would start with all prompts that get some instances to evaluate on. But this again means it's not sample efficient. Now, sample efficiency means you don't want to maybe try out all prompts. Now, if I have to start with all prompts to then discard the worst ones, that means probably some of the very poor performing prompts I could have skipped, which is not possible if you start evaluating all of them. All right, so now we know what we're dealing with and the general setting. What we identify is a lack of method that is both sample efficient, so I don't want to evaluate all prompts, and a method that is query efficient. And query efficient means I don't want to evaluate a prompt on all validation instances. Okay, so what we call HbBoPs is quite simple, the idea. Gives us sample efficiency by doing a BO proposal. That's natural, right? If you want to be sample efficient and you don't want to try out everything in a search space, use something smarter like Bayesian optimization. And the other thing is we speed up query efficiency via Hyperband and then combine the both methods as it has been done in HbO. So prompts are natural language, yet in our case composed of building blocks. You have the instruction, you have the featured exemplars. The question is, how can we learn a good surrogate model mapping prompts to downstream performance? And what we do is actually use a Gaussian process, which most people haven't used before in the prompt literature. But we use what we call a structural aware because it handles instructions and featured exemplars differently, and it's a deep kernel Gaussian process. In the end, it's basically we operate on embeddings of the prompt and have a feature extractor that is a small neural network, and that goes into the kernel of GP, and that gives you a deep kernel Gaussian process. That was proposed like 2016 already by Andrew Gordon-Wilson, and this is what we found to be actually quite good performing. And to get query efficiency, we make use of Hyperband. So evaluating prompts on a validation set naturally gives you a fidelity parameter, which you know from NAS or HbO, which is here the number of validation samples. And we make some adaptations for Hyperband actually, because in contrast to HbO and NAS, the fidelity here, so the number of samples you use to evaluate, this only affects the noise of the objective function, and it does not impact the trend. For example, if you use more training data as a fidelity parameter in HbO, you do have a trend that usually more data gives you better performance. Or if you use more epochs, you usually expect more epochs gives you better performance. Here, this is not the case. Here, the fidelity is directly tied to how noisy is the objective I'm optimizing. And this means you have some adaptations that you can make actually to Hyperband, or some open questions. Okay, now first part, what we call structural aware deep kernel Gaussian process. On a high level, it's quite simple to explain. You have the prompt composed of instruction, featured exemplar. These are the building blocks, and this is natural language. So you start by taking it apart, have the instruction, use an encoder model, a pre-trained one, can be a small one, for example, BERT, and obtain a numerical representation. For example, we use the BERT CLS token embedding that gives you like a 768 dimensional numeric representation of this instruction in natural language. And then you do the same for the fusion exemplar that's composed of K, in our case, and actually 5 examples in a certain order. You again use a pre-trained encoder model like BERT, and you get a numerical representation. Okay, so far so good. Now we have like transferred natural language to numbers, and we can actually learn a regression model based on how well the prompt performed on the validation instances. We continue. You have the encoded instruction. We use a feature extractor, which is just a very small, fully connected neural network. We do the same for the encoded fusion exemplar. And we concatenate and learn, basically to learn interactions between instructions and fusion exemplars. We concatenate and then have another tiny fully connected neural network. And this is then fed as the input to the Gaussian process. So basically you transform your axis before going into the kernel of the Gaussian process. And to give you some detail, like you can see on the top, we call this phi the encoding function. So you would have one, it's actually a very small neural network, right? It's just like D in BERT would be 768 or something like that. So you have a small dimensionality reduction with some very small nonlinearity. You do this for the instruction, you do this for the exemplar, actually 2 different ones, because you want to learn a different representation for instructions and exemplars. You concatenate, and then you do another dimensionality reduction. And then we end up then with an output dimensionality of 10. So the feature extractor is more or less like some not sophisticated, but efficient way to learn a lower dimensional representation of prompts so that the GP actually works well. Because the GP and VO literature tells us high dimensional functions and high dimensional input spaces are something that a Gaussian process does not like very much, right? There has been some recent work, and we also compared a recent modification to vanilla GPs, but in general, high dimensional spaces are not something a Gaussian process likes to operate in. And this feature extractor based on the pre-trained encoder model embeddings are actually an easy way to get a low dimensional representation of the prompts. To show you an example that is actually meaningful, so what you could do is you can just use the raw embeddings of BERT, right? 768. Now, what we did is 250 prompts. The task is GSM-8K, the math task, and the model is Llama 3 8B instruct. And you try out all prompts and you get their performance on GSM-8K together with Llama 3 8B. Color means performance, and yellow is good and purple is bad, I think. And then you split the prompts into a train and a test split, 80-20%. On the top, you can then see if you do TSNE of the raw embedded space, so the 768 dimensions. I mean, TSNE also has its problem, but let's look at the figure. It's difficult to make out like meaningful clusters, or basically closeness in feature space, TSNE reduced, does not necessarily align that much to closeness in performance space, right? So we have grouped together like some good performing ones, but also like some good and bad performing ones. It's a little bit messy, the raw, of course, also due to TSNE. Then what other people proposed is you can do a simple like random projection of the embedded space of prompts, for example, or you could do a PCA in an unsupervised setting and retain 10 principal components. Things still don't look optimal, like how closeness in input space relates to closeness in output space. And then we can do what we do, like train the deep kernel end-to-end, optimizing the parameters of the feature extraction neural networks and the kernel parameters of the GP jointly, and then extract basically the deep kernel latent features. These are also 10-dimensional, and here you can see that you actually have like a smooth transition between good performing prompts and bad performing prompts. And of course, again, TSNE it's not always easy to interpret, but at least visually you can now discern like there's some color gradient, also like how good performing prompts transition into bad performing prompts, depending on where they are in the latent space of prompts. And the interesting thing is that this generalizes to the test set, right? If you look at the test split that was not used to train the deep kernel GP and not the feature extractor, there's still like the general consensus that good prompts are in similar regions as on the training representation. Whereas for PCA, yeah, it's mostly a little bit all over the place, and the same for the raw embeddings. So this to give you some justification of why actually a deep kernel or a feature extractor and then going into a kernel might be useful here. Yeah. Okay. Hyperband for prompt selection, that's actually straightforward. I don't include like pseudocode for Hyperband. I assume most of you in the AutoML community are familiar. So Hyperband extends successive halving to basically safeguard against poor configurations of successive halving. So Hyperband has multiple brackets, and in each bracket, one successful halving run is actually performed. You start with, in prompt selection, some instances, validation instances, some prompts. You evaluate them, and you would keep, based on the halving parameter, the top performing half. And then you double the budget, and you continue doing this until you are left with one prompt, for example. And you now have 4 different brackets, where in each bracket you run successive halving, and that's your Hyperband, right? Nothing changed yet, except for the fidelity parameters, now validation instances. Now, some design decisions that you do have to think about in prompt selection is, first, how do I determine the incumbent? So what's my solution during the anytime process, but also in the end? Because in HPO, you usually could pick simply the configuration that has best validation error. But now in our case, the fidelity parameter is tied to the noisiness of this validation error estimate, and that's bad. So what you actually need to do is you need to return the best prompt always on the highest fidelity. We did an ablation study on this. Otherwise, you might get lucky and like one prompt performed very well on 10 instances simply due to noise or being lucky. But in the end, that's not a prompt that performs good in expectation because you had a noisy estimate of its performance. So that's one open question you have to think about if you use Hyperband. So what's my best prompt? Like I said, you should pick the best performing prompt that you evaluated on the highest fidelity in the end. The other question is, do I use purely random instances for evaluation within a stage for the prompts, or do I use fixed random? So for example, if I evaluate one of these prompts, do I draw 10 instances uniformly at random? Or do I draw 10 instances uniformly at random and all the 8 prompts are evaluated on the same fixed random instances? That means like, do I do a paired comparison or not a paired comparison? And turns out in an ablation study, you should do a paired comparison. Otherwise, it gets messy because you're a little bit comparing apples with bananas, or like can be difficult to actually compare the prompts. And the other thing you can ask is, do I want to keep a superset structure or not? So if I move from one stage to another stage in a bracket, so now I have 10 instances, now I move to 20, do I want the 10 previous instances to be included in the 20 ones? This is what we call a superset structure, right? Or do I draw completely new ones, which you could do? And it turns out that if you use a superset structure, that's usually better for performance, especially if your LLM evaluation is close to deterministic. So if you usually get the same output, like not the natural language output, but the score would be the same, then it makes sense to have a superset structure because you can actually cache the evaluations, right? That means the 10 that you would include in the 20 of the next stage, you don't have to evaluate again. You can simply look up based on caching the evaluations, which means you get some speed ups again. All right. Now, a la Bob, which was like proposed in hyperparameter optimization, we now just combine hyperband with the BO proposal based on this deep kernel GP. This means you run hyperband, but at one point you start proposing prompts not uniformly at random that you evaluate, but based on a Bayesian optimization proposal. And we make use simply based on a BO proposal based on the acquisition function, based on the expected improvement with some minor modifications. So if I have my data set at a time point t and at a fidelity, so validation instance level b, for which I want to propose prompts, we say we pick the prompt that has, in expectation, the highest improvement over the current incumbent. So we min would be the best performing prompt so far, but actually evaluated at the same fidelity level. So that's the incumbent performance that you are comparing against, and f of z of p would then simply notation for this is the posterior predictive distribution of the Gaussian process based on the embedding of prompt p. And you optimize the expected improvement, find the next prompt for evaluation. And in our setting, since we work in although it can be large, but a discrete search space, you can actually optimize the expected improvement just exhaustively. You don't have to use numerical optimization techniques. You just try out all the prompts. And computing the expected improvement is fast, so it doesn't matter here. And yeah, on the right-hand side, like the complete hyperband with BO proposal, but we're not going to go in detail about that. Like I said, it's basically you follow the hyperband schedule for proposing prompts and validation instances, but you start to propose prompts based on a BO proposal within hyperband. Okay, experiments. So we compared the method on 10 benchmark tasks. First one is A2ARG's reasoning challenge. This is multiple choice question answering, which is publicly available and often used in academic benchmarks concerned with prompt optimization and selection. The other one is GSM-8K. Most people probably also know multi-step math problems. And the other 8 ones, we took inspiration from what MiPro, EASE, and Triple, like the competitors, mostly used in the benchmarks. And they are from Big Bench or Big Bench Hard or instruction induction. And they are like, find the antonym to a word, find the large animal from a list of animal, negate a word, what's the second letter of a word, and so on. So different natural language tasks that you might find reasonable or not, but at least that's like what existing works benchmarks on in the prompt optimization and selection literature. For generating a prompt pool, we simply construct 5 instructions, which we assume is probably practically feasible, 5 per task. We do this automatically using APE in its forward mode. Basically an automated way to come up with instructions based on an LLM. How this works is you give an LLM input-output examples for a training task, and you ask it, given this input and this output, what was probably the instruction. Like this is how APE works. And we use Claude Free Sonnet and use 10 input-output examples to get the instructions. And to get the fusion exemplars, where we have 50 per task, we simply sample 25 sets of 5 input-output examples from the tasks. There's a k-messing training set, and then commute the sets to have like some ordering difference in the fusion exemplars. And then you just combine the prompts, and this gives you the final search space. Okay, for LLMs, we use Claude 3 Haiku llama 3 being struck or Mistral 7 being struck, which at that point when I did the experiments were like, of course, not the cutting edge models, but the cost effective, quite well performing ones, right? They are not the 80 billion parameter models, but they are models that you usually get good performance if you tweak around the prompt a little bit. Okay, evaluation protocol means how well benchmarks run. So each method is allowed 25 what we call full fidelity. So for a task, you have a validation set, and we allow 25 full fidelity evaluations, which would mean an LLM is allowed to evaluate a prompt on all validation instances, and then I could evaluate 25 based on what the cost would be to evaluate all 25 prompts on all instances. But if I'm smart about how I select my instances, I can be much more efficient, right? And don't evaluate all prompts on all validation instances. Cost metric is, in our case, simply the number of LLM calls, because we want to average over different LLMs and also different validation set sizes, and then did not use actually token cost, which could be another metric, but it's easier interpretable if you average over different costs per token. And repetitions, 30 repetitions, and prompt evaluation metric is simply exact match scoring function after some sanitation of the output to make sure that you can actually compare the ground truth Y to the output Y of the LLM. Okay, baselines and competitors. Baselines, a simple random search, propose prompts uniformly at random. Use vanilla Bayesian optimization. So just Bayesian optimization on the 768-dimensional BERT embedding. High-dimensional BO, which is basically vanilla BO with some tweaks how we train the GP. That was proposed last year by Karl Hafner, figuring out that if you do MAP estimation of kernel and likelihood parameters of the GP, in high dimensions, you get better performance if you treat the priors to adjust like for the dimensionality, basically. And then there's another baseline that is Bayesian optimization with the PCA. So you use an embedding of prompts and you do a PCA unsupervised, and then you do a vanilla GP and do a Bayesian optimization proposal. These are baselines because they have not been like published, so to speak, in the setting of prompt selection. And the competitors are then actually EASE. We talked how this works. Neural UCB based on an encoding of prompts. MePro, which is tree parser estimator based on categorical indices of prompt. And then Triple, which is simply successive halving. And Triple GSE, which learns a model to predict prompt performance based on embedding of prompts to use it to discard the poor performing ones. And then ours, which has this Gaussian process, deep kernel Gaussian process, and we operate on separate embeddings of instructions and exemplars. Okay, high-level results. On the left, you see validation performance, which you optimize, right? And on the right-hand side, you can see an unbiased performance estimate on a completely held-out test set. To actually see like how well does the optimal prompt that you find during selection perform on a test set. And on the x-axis, you can see the number of LLM calls, where like 1.0 means 25 full fidelity prompt evaluations. And full fidelity means 25 prompts on all validation instances of a task. And this allows us to actually average over tasks. And on the y-axis, you can see the mean normalized validation error. And we normalize per benchmark task and LLM based on the best performing prompt and worst performing prompt. So 0 means best performing prompt, 1 means worst performing prompt. And then again, you can average over different benchmark tasks in LLM. And the high level result is what you in general would expect, like the full fidelity methods, the one that are mostly the same until 40% of the budget, because they use 10 prompts at random for the initial design. They start to be different after 10 prompts, right? We actually find that the high dimensional BO variant performs quite well. And then the PCA BO variant followed by MePro, which is actually interesting. So you can learn something from simply categorical indices of instructions and exemplars. It's better than the random search in blue, but it's not as good as a actual BO. And then we have vanilla BO and EASE, which are not so strong performing as a PCA and then BO or high dimensional BO. And for multi-fidelity methods, we mostly have like triple, successive halving, and GSE. And we can see you get speed ups because you evaluate prompts on fewer instances, right? And actually in the end are very well performing, with the simple successive halving baseline performing very well. And finally, you can see in brown our method, which is, yeah, here the superior one in any time, but also final performance, mostly due to at the beginning, you make quick progress because you try out few prompts on few instances, thanks to Hyperband, but you still have good performance in the end because the BO proposal starts to kick in, and you actually, in the end, figure out which prompts are meaningful to evaluate next. Looking at the test set, it mostly generalizes, but we can also see that what you see during validation, like doing optimization, is of course not directly translating to the test set. So in general, random search and BO actually, with respect to test performance, vanilla BO perform the same. Still, high-dimensional BO performs slightly better, but also we can see that our method in the end, still we are like, there's a numerical difference and we are slightly better, but the successive halving baseline actually in the end comes close. But you do get the initial speed up in how we ran Hyperband compared to how they run successive halving, because we do not evaluate like all prompts at the beginning. Okay, ablation study, which might be interesting. If we start with the random search, again, the same plots, so I don't have to tell you what's on the x-axis and the y-axis. If we start with the random search in blue and move to BO, we've seen this before, you get some improvement on the validation set. Now the question you can ask is, if I start to do what we do, a deep kernel, but not structural aware, so use a neural network as a feature extractor on the embedding of prompts, but do not split instructions and exemplars. What's the performance I get in BO? That's the purple one. It's actually quite good and beats vanilla BO. It also beats the high-dimensional BO one slightly, which I haven't included here. And then we can compare like what do we gain by the structural awareness, by like embedding instructions and feature exemplars separately and having like the slightly more sophisticated feature extractor. This is in green, which gives you another performance boost. And then orthogonal, you can see what's if I simply run Hyperband, how we did it, the darker green one, and compared to running Hyperband with our BO proposal. Now you can see in the beginning, the speedups are mostly due to Hyperband, right? In the end, the good performance is the BO part kicking in. Things mostly generalize on the test set, although I do have to say, like, it's not easy with generalizing to the test set. We can talk about this later. So turns out that on the test set, the structural aware, like embedding instructions, feature exemplars separately, still is slightly better, but the gap like becomes less than on the validation set, which is doing optimization, right? But in the end, the Hyperband with BO proposal is still robustly performing well. Another experiment we had is, well, we use simply BERT, the CLS token embedding, to get a numerical representation of prompts. Does it matter which encoder model you use? We did a small ablation study where we simply compared BERT to Distill Roberta, which is also based on Roberta, but a distilled version, and in PNet, they are all encoder-only models, right? Some different encoders, different pre-training procedures. In the end, if you look at the validation and test performance over all the 30 benchmarks, so all the benchmark tasks and 3 LLM, it doesn't matter much, I would say. Like they are very reasonable close if you compare the numbers. Maybe you would think that the still Roberta version is slightly better actually, but in the end, it doesn't matter much. So it also doesn't matter much like which encoder model you use before having the feature extractor. In the end, none of these is like trained or fine-tuned to tell prompts apart on a downstream task, right? This is what you learn with the feature extractor and the GP. So the only thing your encoder model has to do, like provide some semantic information on difference on prompts. And likely all of them do this reasonably well. So it doesn't matter much which encoder you use. Okay. Conclusions. So we combined actually techniques from AutoML. Like what we did is basically BoP for prompt selection. And this allows us to do efficient prompt selection for a black box setting. We did some deeper dive into how can we actually model prompt performance with the GP. And yeah, have this adaptive fidelity scheduling thanks to Hyperband. And we outperform actually state-of-the-art methods, the NIPRO from DSPy, EASE and Triple. The deep kernel might be interesting on its own, I believe. Maybe you could also pre-train the deep kernel or do transfer learning, because currently the GP is trained online, which is interesting. Like the question, in general, having access to natural language in your search space and transferring it to a high-dimensional space means it's an interesting playground for high-dimensional BO in general, or like how to get BO methods working in this setting. Hyperband is straightforward, I would say, with some minor modifications that we've discussed. Overall robust and good performance, I would say. And you do get speed ups by not evaluating all prompts, right, on all validation instances. Okay. And like I said, this is actually also a paper that shows prompt selection optimization can be an interesting venue for AutoML methods, because we spent a lot of time in the last years as the AutoML community to build efficient algorithms to identify well-performing configurations or optimize them. So why not make use of them in this other related field, where although your search space is natural language, still you can get them to work, right? Some future directions, you could look at richer prompt space. We focused only on instructions featured exemplars. So output guidance, formatting constraints, they were all ignored. But usually prompts include this, right? Like format in JSON XML tags, but also output guidance, or even more. You could extend to multi-objective, because the number of future examples, so the K in an exemplar, but also the overall prompt length, means you have higher latency when you use the prompt. And this usually you would expect to conflict with prompt performance. And we focused on this finite search space. So this means somehow we have access to a space, prompt space before, and then we want to quickly identify the best performing one, but we don't change it during the selection process. But you could, of course, integrate this into an end-to-end prompt optimization pipeline. You could use like ideas from prompt breeder to actually do a Bayesian optimization and not selection thing, where you would like mutate existing prompts that are well performing and come up with new instructions on the fly, right? We didn't do this, but in principle, the surrogate modeling and the hyperband part are more or less orthogonal to this. Is the search space fixed a priori, or do we actually evolve it over time? And another thing we can have a look at is actually performance estimates can be very noisy if you use few validation instances, which is an interesting finding on its own, I would say, because some paper, the East paper, for example, they benchmarked on 20 validation instances and then figured out that they have some serious generalization gaps to the test performance. But if you look like at how noisy performance is, if you only use 10 or 20 validation instances, it's probably no surprise, because you cannot make an informed decision on the validation score because it's so noisy. But this is something probably that you could investigate further or keep in mind in general with LLM evaluation. All right, that's it. I do have some references in the appendix, but I'm slightly over time already, I believe. So happy to answer any of your questions.